Now that we've re-established y and x, let's continue down the spatial trail. Lat long or other coordinate systems give us a spatial connection to the Earth, to the planet. It allows us to establish rigorous, repeatable, shareable means of collecting and sharing spatial location information. And the other coordinate systems, we've used some in GIS already. Things like state plane or UTM, all these other kind of systems that are out there. They have their own definitions, their own ways of functioning, their own structures and kind of shared language. But everything, whether it's lat long, whether it's any of those, whether it's any of the many projections or coordinate systems that we haven't used, all have to relate back at the end of the day to some established, agreed upon measurement of what the planet actually is. What is this orbiting, spinning, roundish thing that we're all standing on talking about? And how we refer to that process, or how we start that process, is that we have to start with our understanding and our definition of that geoid. Well, not that geoid, our geoid. It's the true shape of the Earth. The Earth is a geoid, technically an oblate spheroid. The geoid means Earth-shaped. We're really good at naming things, us, humanity. So what shape is the Earth? Earth-shaped. What shape? You might say, oh, well, does that mean Mars is Mars-shaped? Absolutely. Mars has a Marsoid. We have a geoid. The geoid's an oblate spheroid, meaning that it is kind of a squished sphere, and our squished sphere is a little bottom-heavy, which sometimes leads people to call the planet pear-shaped. This is the shape of the Earth. It is certainly not flat, but it's also certainly not a sphere. It's much more complex than that. The geoid is a gravity-based model that seeks to model the actual shape of the Earth. And what's important to recognize about this is that we have many different, not only definitions, but many different constructs, understandings, measurements to create the geoid. The geoid is not static, it changes over time. And it changes because it's actually changing. The planet is actually changing shape subtly, but it's happening. But also we have gotten better at measuring it over time. We have gotten better at taking data or collecting data with different tools, different technologies. The satellite era has accelerated our understanding of the geoid. So really, at the end of the day, the Earth is just a lumpy space potato. Watery space potato, wobbling out around the sun. And we decide to try to measure it as best as we can, constantly. Refer to that bulge in the southern hemisphere. So the southern hemisphere is a bit bumpier. I don't know. Geodesy, the study of the shape and the size and the function of the Earth, is really fascinating. And it underlies in a way that's often hidden in our GIS work until it becomes an issue, until we start talking about, well, what coordinate system are you using? What projection are you using? How are you measuring the size and the shape of the Earth? How old is that data anyway, and how are you using it? At the end of the day, it's really fascinating. There's a geoid model. Reds in this model are higher elevations than the mean on this geoid. Blues are lower than the mean Here's it zoomed into the lower 48, middle of North America here. What this scale shows, take a peek at that bullet on the bottom, is that geoid heights in this representation, this is Geoid 1996. These geoid heights represent pretty much all below mean geoid, below the mean geoid height elevations. So from the magenta, which is 51 meters below geoid mean height, to 7.2 meters below geoid mean height. And what that's saying is that if we think about the geoid, if we remove and strip off all the water, all the vegetation, everything else, and we just consider it as a ball of space rock, and we are measuring the gravity of that space rock, at some point there is a mean elevation, and North America is, or at least the conterminous US is below that mean elevation. And you'll note that it's not corresponding with mountains. There are maybe some things you can squint at and see a mountain range, but it's not actually related to topography. The geoid height, here's WGS 84. So this is the Geoid 1984 of the World Geodetic System. And our areas, high and low, do not correspond with topography. And this is a really important thing to emphasize. When we're thinking about the geoid, when we're thinking about the size and the composition and the weight and the gravity of the planet, the topography that we see, our mountains, our hills, our valleys, what we can see on the landscape, has no relation to the geoid heights. They are detached. They are separate. And that's because the geoid itself, the planet itself, has a lot going on internally, a lot going on underneath our feet, underneath everything. I mean, all the way down to that spinning molten iron core that is influencing the size of the geoid, that is influencing the weight and the structure and the function of the planetoid that we're on. I guess we're on a planet. It's not a planetoid. We're a real planet. And our real planet has variations, has dips and bumps. See, the peak heights of the geoid are actually in the North Atlantic and in the Indonesia area, north of Australia. See that bulge in the southern hemisphere, southeast of Africa, south of South America. See that there are low points on the geoid right off the Indian subcontinent, around Antarctica, and North America, central China. So when we think about the geoid, when we think about the planet that we're on, it has undulations up and down just based on its structure. And those structural undulations, which are separate from topography, give it its different weights, give it its different bulges, give it its lovely pear-shaped appearance. Now, you notice that in those previous two, let's hop back. Here is Geoid 1996. Here is Geoid 1984. And if you kind of squint, the scales are a little different, but if you look at it carefully, you can see some differences. Certainly there's a little bit more detail in North America in 96, probably because Geoid 96 was at a better resolution. So we see some differences. And if we look at this chart, which is comparing two North American specific datums, so two North American specific measurements and understandings of the size of the planet, we can see even bigger shifts. Between NAD 27 and NAD 83, locations make big changes. So these are changes in distance in meters. And if you're in Michigan or Indiana, you can use your NAD 27 measurements just as good with your NAD 83s, but don't do that in Colorado or Idaho or Washington. As we operate with these geoids and these different understandings and these different functions of Earth measurements, as it turns out, we don't always need to model the geoid perfectly. We can generalize it to an ellipsoid or a spheroid. So if we think about our whole stretch here of everything that we've been operating with so far, we start with the geoid. That's the true shape of the Earth. That is what the Earth is shaped like. And we understand that shape differently based on our technology, based on our measurement techniques, based on how we're focusing and operating with that geoid. So we get changes in Geoid 84 or 96 or 2020 or whichever one we're using, because we take new measurements, we refine our data collection capacities, we have better or higher resolution data, and the Earth changes. All of these things work together and we get an answer. This is the geoid. And then we generalize it. We say, okay, this is the geoid, and this is an easier way of referencing the geoid, called an ellipsoid. There it is. Now, the ellipsoid recognizes as a shape that the Earth is not a perfect sphere. It has two primary functions, or two primary measurements. We've got the semi-major axis, which is our equatorial radius. Then we have a semi-minor axis, which is parallel to that, or parallel to the rotation axis. Earth, remember the Earth's tilted a little bit too. It's not straight up and down like that. That's a problem for a different class. Our ellipsoids then generalize the geoid shape. Our ellipsoids take that very complex geoid and turn it into something that's a lot easier mathematically to handle. Right? We can definitely handle an A and a B and determine a flattening of A minus B over A. This makes it possible to model computationally for anybody. Certainly, there are very detailed computer models about the geoid that we can't pop into a GIS. But we can pop an ellipsoid into pretty much anything. And you can see here, our ellipsoid in the dashed yellow lines is nicely surrounding our geoid, but it's not a perfect fit. In some places, it aligns very nicely, and in some places, it aligns very poorly. So we make lots of ellipsoids. And here's where our specific use cases start coming into play. I could make an ellipsoid that is good for me at point B there on the lower left. You could make an ellipsoid that's good for you at point A in the top right. The geoid, in its variances, can be reduced in a bunch of different ways. And so sometimes it's easiest to reduce it so that it is best fit for everywhere, but sometimes you want it to fit best where you are. These different ellipsoids allow us to do that. And so we can see from this example, if we were to follow the geoid, our center line that says geoid there, at some points we might be above the ellipsoid, the reduced generalized representation of the geoid, and at some points we might be below the ellipsoid. Then the surface, the actual topographic surface of the planet, might also be above or below that geoid or the ellipsoid or both. In this case, it is. Our surface is way up there. Doesn't have to be that way. The topographic surface can be above or below the ellipsoid or the geoid. The ellipsoid can be above or below the geoid surface. These surfaces, these different Earth surfaces, all represent something very important in our understanding of the shape and the size and where we are on the planet, but they are all very different, and they all have very different relationships between each other. Topography is independent from the geoid. The geoid is generalized to the ellipsoid. How you do that generalization means that it's either best fit for the whole geoid or best fit for a certain area of the geoid. And then the ellipsoid can be above or below the topography. The geoid and ellipsoid are related in terms of math. Topography is independent of them both. Here's another look. So we can see all of these different combinations where the terrain or the topography is above these different components, or the terrain or the topography is below some of these components. And we've added in a new surface here, because why not? What about the water, you're thinking to yourself? When I look at a picture of the Earth, I see a lot of water. Yes, you do. There is a lot of water on this planet. And where the topography is low, the water likes to hang out. And when the topography is low across big stretches, we have lots of water. Call that an ocean. The ocean, or mean sea level, is roughly the same as our mean geoid surface. Not always, but roughly. Mean sea level, what does that mean? Well, another way of thinking about our geoid is to think about it as a best fit for our Earth's mean sea level surface. You can imagine that pretty easily. If you look at the planet and you see an ocean, that's the mean sea level surface, roughly. And over these open oceans, geoids and the mean sea level are about the same. Continental areas, it's more difficult because, well, we don't actually have an ocean there. So there's a little bit more variance. But we know if you had a GPS device, or if you had some kind of perfectly accurate instant elevation measuring system, that our oceans are at different elevations. If you're at sea level on the Pacific, it's different than sea level from the Atlantic. But this is another one of those surfaces we might think about at times. All of these surfaces provide us an understanding of how the planet operates. All of these surfaces give us an idea of what the function of the planet is. And while terrain or topography is detached from the geoid, mean sea level is much more closely related. All of these lines, all of these surfaces, all of these components play a role in our understanding of the planet and of our understanding of location. And when they come down together, understanding all of these things together helps us understand where we are, what is going on the planet.